Well, today, let's begin. If we just take a quick look at where things are, homework 11 is due on Friday, and then Monday of next week is when the final project report is due, and then the last thing of the semester is homework 12, well, the second to last thing of the semester. Homework 12 is due on Friday, then we have the final exam, which is scheduled for Friday, April 30th. Okay, now a word about the project. I have finished grading phases 2 and 3. And so the final report needs to be more than just cramming together phase 1, 2, and 3. Remember that when you submitted phase 1, that included, well, it's supposed to include a brief write-up where you explain your rationale and your decision process for the demand estimation. Part 2 didn't require any write-up for the draft submission. I just wanted 2 maps. But for the final report, there is a write-up that needs to accompany the work that you've done for phase 2. And same thing with phase 3. There should be a written explanation of the entirety of the project, including the cost analysis that you're supposed to do. And so that's, my suggestion would be to read through the assignment description one last time before you click submit on Monday, just to make sure that you've got all the pieces that are supposed to be there. I've given some feedback on phase 2 and phase 3 where I thought that some corrections were needed, and then of course in Monday's class I showed you an example of a nice looking annotated map. Today we're going to continue talking about hydraulic jumps and then move on to talking about underflow gates. And we ran 1 minute long in Monday's class, and so I intend to let you out at least a minute early today. So that's something to look forward to, right? Okay, so last time we talked about there are some empirical methods of estimating how long a hydraulic jump is going to be, and that the key parameter that dictates the length of a hydraulic jump is the Froude number upstream. That is how supercritical it is upstream is going to lengthen the jump. It's also going to increase the downstream depth, of course. If you have a very shallow upstream depth, then the downstream depth will be deeper because of the way that momentum depth diagram works. Now here's the example, and rather than pausing and let you go through the calculations on your own, I'd rather that we save a bit of time for the last example we're going to go through today. And so what I'm going to do is just show you the solution to this one, and we'll talk through it together. But just to save time, I won't ask you to actually do the calculations yourself, not for this one. So what we're told is that there is a channel that has a flow velocity of 5 meters per second, and it's 25 centimeters wide. So that's the width of the channel. And we have the depth upstream is 10 centimeters, and we want to know the depth downstream. So, our solution process is going to be that we first calculate the Froude number, because with the cross-sectional shape of this rectangular channel and the velocity, we can get Q. So that goes into the Froude number equation. T means the top width. A is the cross-sectional area. So we have everything we need for the Froude number, and then the Y2 depth is going to be some function of the Froude number and the initial upstream depth. So here is the solution for that. Starting off with the given data, I calculated the cross-sectional flow area with the width and the depth that are specified, and the Froude number of 5.05. We can calculate, first of all, what is going to be the depth downstream. So here's the Bellinger momentum equation. This variation of it is using the Froude number and the upstream depth to predict what the downstream depth will be. So it started off 10 centimeters deep, and it's going to jump up to a depth of 666 centimeters. Now, have I done that right? Yeah. 66.6 centimeters. Yeah. Okay, so this is going to be the downstream depth, and the reason why we need to know that is if we go back to the figure on this nomograph, what it says is you calculate the Froude number, and in our case it's 5. And so here between 4 and 6, we're going to go up with the known Froude number of 5 and find the point of intersection of this curve. So here this curve goes over to the left now, and 6.1 is the numerical intercept there on the vertical axis. So 6.1 equals the ratio length of jump divided by y2. So the way that we use that is we multiply 6.1 by y2, and that'll tell us the length of the jump. Because it was saying Lj divided by y2 equals 6.1, so we just rearrange algebraically, multiply together the known downstream depth by the factor that we looked up off the vertical axis of that nomograph, 6.1, and so it tells us the jump should be 4.06 meters. And what that length is talking about is the overall distance from when the jump begins until it reaches the stable, uniform depth downstream that's dictated by the channel and the normal depth. And so how long from when the jump starts to when it reaches equilibrium and it's flowing at the normal depth again. Okay, so this first method suggests that that length would be 4.06 meters. But it's hardly the only word on the subject, because we also have this function that uses the tan h, and you can use that in Excel. Some calculators also have it. So here the length of the jump relies on the upstream depth and then 220 times tan h of the Froude number upstream divided by 22. So you can see here the substitutions that I've done. I've got the Froude number of 5.05 divided by 22, so that is 0.2295. And then if you do the tan h of 0.2295, you get 0.2256. Now it's just coincidental that this is both 0.22. The tan h function isn't always going to be essentially the output of it nearly the same as what went into it. So don't expect that just because this was 0.22 and 0.22 went into it that you might as well just skip the tan h function, because that's not always the case. But this other method of predicting what the length of the jump would be says that it's going to be 4.96 meters. And then we had this third approach that was it said another method. And so if we just use kind of a midpoint A value, if we say let's have A be 5.5, then that other method, which says it's some fraction of the change in elevation, so it finishes at 0.666 meters and it started at 0.1 meters, so that predicts that the jump length is going to be 3.11. Now, what it actually is in some cases an art as much as a science, because it can be pretty subtle, the changes of depth as you're approaching. What we're looking for is when the depth approaches the normal depth. So here the flow is back to the normal depth. This last part of gradually varying flow, you're going to notice just a minuscule change in the water depth. It requires quite a lot of precision with a pin gauge to see how much the flow depth is changing from this point over to this point. So these are just kind of estimates that are useful in predicting how much of a stilling basin length would be required. Remember, the stilling basin's purpose is to prevent scour from occurring downstream. It's kind of a location that the hydraulic jump can set up, and it's armored and concrete, and there may be blocks in there to help absorb some of the vigorous impact of the water that's going through the hydraulic jump. So if we wanted to understand how long the stilling basin needs to be, then we'd want to calculate what's the length of the jump. All right, now let's talk about gates, underflow gates to be specific. A gate may be something that's just as simple as a metal plate with a bit of bar welded onto it as a handle. And you can see that this metal plate is fit into a metal frame, and most likely the water would be behind this gate, because what that would be doing is the water would be pressing on the frame to keep the plate into the frame. And someone who's trying to regulate the flow would simply open up the gate using the handle, open it up a certain amount, and then that would dictate how much water is flowing out under the gate, maybe into an irrigation ditch that's going to be used for watering a crop. The problem is that this metal plate may be fairly heavy, and so when you get beyond a certain size, it may be necessary to put in a crank, and it may have gears, and the length of the crank maybe would give you some leverage to help lift the gate, or it may be that they put an electric motor on the top. But Waterman is one of the manufacturers of gates like this that's used a lot out in the western part of the United States in irrigation canals. And so there are a lot of applications both in agriculture, but also in water and wastewater treatment, where you may use gates as a flow regulation device. It is also common to have gates that are on a frame that it can rotate. A radial gate like this avoids the issue of a big hydraulic pressure forcing the gate closed. And if you think about the force of the water acting on that gate, maybe pressing it up against the frame so that there's so much friction that it makes it even harder to lift the gate upwards. You'd need to lift the gate up not only enough to overcome the weight of the gate, but then there's also the frictional effect of the gate sliding up against the frame. And if the frame has rubber on it to help prevent leakage, then that would just make it all the more difficult to lift the frame. And so a radial gate like this kind of avoids some of those disadvantages, and I'll show you a cross-sectional view in just a minute what that looks like. But the gate discharge can be calculated with the energy equation. At the simplest look at things, if we were just at first going to neglect the effect of energy loss, then what we would say is that the amount of specific energy upstream can be related to the amount of specific energy downstream, assuming that there's no losses. And there are losses. We'll get to that in just a moment, how we account for them. But specific energy is conserved through the gate in this first conception of what's happening. And of course, we know that the water is pooling upstream because this gate is interrupting the water from flowing at the normal depth. And so there was pooling that occurred upstream to enable a fast velocity of water to go under the gate. And so eventually it comes into equilibrium and the flow in and out of the control surface is equal. And I think I mentioned in our previous class meeting that the height that the gate is opened, here it's called y sub g, that is larger than the eventual flow depth under the gate. That there's some further contraction that occurs because the fluid continues to accelerate due to the pressure that's behind it. And so the water doesn't stop accelerating immediately after the water goes out from under the gate. Now this may be a little bit extreme where it's showing the contraction quite a bit further downstream. It may be faster than what's illustrated here, but we can relate the downstream depth. It's some function of how high the gate is open. So the C sub C is referred to as a coefficient of contraction. Now most gates like this are the full width of a channel, or at the very least, even if they're not the full width of the channel, they're rectangular in shape. And that makes it a little bit easier for us to do flow calculations because if it's a rectangular shape, then we can calculate the flow per unit width under the gate. So lowercase q, remember, flow per unit width is simply the volumetric flow rate divided by B, which is the width of the channel. And what this is telling us is that the upstream depth y1 and the downstream depth y2 that the ratio of those, the magnitude of those different heights can be used to calculate the flow per unit width. So we could rearrange this to solve for the flow rate. Now the coefficient of contraction is usually about 60%. And so 60% is going to be the height of the water after it continues accelerating and drops down beyond the opening of the gate. And This all would be true if there was no energy loss. But because there is, we are going to refer to a coefficient of discharge in just a moment. So here's that cross-sectional view of a radial gate that I was mentioning, and what you can probably visualize is that the hydrostatic forces that are acting on this radial gate point inwards towards the center of rotation. And so since the direction of the force is towards this rotation point, that means that there isn't going to be any moment distance or any kind of force that prevents it from being lifted other than the weight of the gate itself. There isn't that same frame pressing up against the gate pressing against the frame and additional friction issue. Gates are used for regulating flow. Broad-crested weirs are useful for quantifying the flow, but gates are more useful for controlling it. And when we were talking about weirs, I mentioned that trash and sediment can accumulate upstream because you've got this big, essentially a wall in the channel, and so anything that's floating, the water that's being moved downstream is carrying debris with it. And if you have a big barrier like a broad-crested weir, then that debris can settle out in the front face of the weir. In a gate like this, there isn't going to be sedimentation because any sort of debris that maybe would accumulate is going to be swept through the gate because the fluid is accelerating and the velocity is actually faster upstream of the gate. Rather than the velocity stopping down at the base of the gate, the velocity is going quite quickly, and so it's self-cleansing in that sense. Now, here's the orifice equation that does take energy losses into account. And you'll notice here the coefficient of discharge is a factor that's going to account not only for the contraction that occurs, but also energy losses related to countercurrent flow, potentially turbulence, and the fact that the water velocity vectors are having to change direction as the water was flowing to the side, and then it has to flow downward. In the same way that there's energy losses when the channel contracts or expands, there are also energy losses when the flow, that the height of the flow goes from one height to another. So the coefficient of discharge takes both of those things into account, the ratio of the upstream to the downstream flow, and then also the contraction that's occurring. And so the overall orifice equation, now here you'll notice that the height that the gate is open, in our textbook that's referred to as W. In a lot of other references, I think including the FE manual, that is just simply called Y sub G, meaning how high the gate is open. But our text calls that vertical distance, the distance from the bottom of the channel to the opening of the gate. It calls that W. And so the orifice equation is the discharge coefficient, B is the width of the gate opening, W is how tall the gate opening is, and so this is a cross-sectional area, right? And then square root of 2GY1. And so you'll notice I've labeled this as the orifice equation because that's essentially what we have. The same orifice equation we saw last semester in fluid mechanics when we had that jet of water coming out of the clear plastic cylinder. So it's the orifice equation. Now, in the case of last semester when we were using the orifice equation, we said it was from the center line of the opening. And this formula is saying, let's just go all the way down to the bottom of the channel for our representation of height. And so part of that difference is built into the coefficient of discharge that would be developed for a gate. All right, so I'd like to pause now, rest my voice and rest your ears, give you a chance to calculate what is going to be the flow through the gate that's depicted here. And so the canal width is different in this case from the width of the gate. So oftentimes the gate is the full width of the canal, but here it's not. So don't confuse the canal width with B, the gate width. We have the opening height is 45 centimeters, and so that is how far is it from the bottom of the channel up to the edge of the gate. So 45 centimeters. And then after contracting, here at this location, the downstream depth is 27.5 centimeters. So what I'd like you to do is I'd like you to calculate, first of all, the coefficient of contraction. Then when you have the coefficient of contraction, you can determine C sub D, the discharge coefficient, and then substitute all of that here into the orifice equation to find out what's going to be the flow going down under the gate in this situation. Okay, I've changed this formula. Before I had this term was Y sub G. That means, the height that the gate is open by some texts. But, here this figure is referring to the gate opening height as W. So I changed this term to be W so that it's at least consistent on the same slide. All right, so the order of operations here is first calculate the coefficient of contraction, then the discharge coefficient, and finally the flow rate, Q. So let me show you that. All right, you can see that the water upstream of the gate is 2.7 meters deep. Then the gate opening is 0.45, and after contraction, the flow depth is 0.275. So the coefficient of contraction is 0.611, and then the discharge coefficient, 0.5822. And finally, substituting that into the orifice equation, we have 0.5822, which simply means that we can't actually convey as much flow through that opening as we might expect because of the countercurrent flow directions, the turbulence, the energy loss. Using the orifice equation by itself, uncorrected, it would over-predict how much flow is actually getting through that opening. So that's why we put the discharge coefficient in there. Now B is just the width of the gate. It's not the width of the whole channel. And this problem had specified that those two distances were different. So the canal is 4.3 meters wide, but this gate is only 1.5. So we use the physical width of the gate itself for B. And then this final parameter, W, is how high the gate is open, 0.45. And then, of course, we have square root of 2G and then the flow depth upstream. So 2.86 cubic meters per second is how much we can expect to see coming through that underflow gate. Any questions before we move on from this example? Now, on Monday, we talked about hydraulic jumps. And I told you that how much you open the gate controls the location of the hydraulic jump. And remember, the ideal situation is that the tailwater rating curve and the jump rating curve are on top of each other. And all that means is that the flow depth that's naturally going to occur in the channel downstream, so in other words, Manning's equation, solve for depth, that depth is the conjugate depth of the flow after contraction after the gate. So think about the two things that are, well, I guess there's three things happening in this figure. First of all, working from the upstream direction, the water pooled a little bit compared to its original flow depth because of the gate. So this water level is governed by how much flow can get under the gate. So there's this depth, but then the water contracts down to Y1, which is the upstream depth prior to the hydraulic jump. And then the hydraulic jump goes up to Y2, which is also the normal depth of the channel. If that's not the case, then we have situations where the hydraulic jump is either closer or further away from the gate. To find out how much you can open up the gate, then you first want to find out whether there's even going to be a hydraulic jump downstream of the gate. Because if this was a steep slope and the normal depth is going to be less than the critical depth, then that would mean the steep slope isn't going to have a hydraulic jump. So the reverse of that is just saying you'll only have a hydraulic jump if the slope is mild, meaning that the slope is less than the critical slope or that the normal depth is greater than the critical depth. Now, how much you can open the gate without drowning the jump is going to be it's going to take the coefficient of contraction into account. So y1 would be the upstream jump depth, divide it by the coefficient of contraction, and then that will tell you how wide the gate can be opened. You know, how big is W. Now here is the Bellinger momentum equation, but it's a little bit different than I've showed you before. In the past, we've been solving for y2, right? You would be given a y1 upstream jump depth, and you'd be solving for the unknown downstream jump depth. But here, this version of the equation has been rearranged to solve for the unknown y1. And so this is solve for y1 in terms of y2. So here we want, if we know what the downstream deeper jump depth is going to be, we're going to find out what's the sequent of that. So what's the upstream depth? And if you close the gate, so if W is less than that limit, then that's going to push the hydraulic jump further away. And if you open the gate more, then that brings the hydraulic jump towards the gate. So these relationships, the jump can run away from the gate or it can approach the gate until it drowns the jump. Now, again, the ideal case is just that the hydraulic jump occurs immediately after contraction. And it can do that when the normal depth downstream equals the sequent depth of the hydraulic jump. Here in this example is what I wanted to reserve a little extra time for us because there's lots of stuff that's happening here all at once. We've got a hydraulic jump that's happening, and we'll be able to calculate the depth after the jump by, let's see, I think in this case we know the width of the canal and the width of the gate is the same, and we know the flow rate that it's carrying, and so we want to find out how much can the gate be open. So what is W that will allow you to not drown the hydraulic jump? So first of all, we have to calculate the normal depth downstream using Manning's equation, and we're going to set that equal to the y after. So we're assuming like the ideal case. Remember that ideal case where the jump happens immediately after contraction. So the steps here, first of all, we've got a rectangular channel with B, the bottom width is 5. We have an unknown flow depth, so we're solving for y. The n value, it says, is 0.02. We know the slope of the channel is 0.3%, so then that's also going to go into Manning's equation. So with Manning's equation, you can solve for the flow depth. And then once you have that, that's y after that you're going to use to calculate y before. But you'll notice that in order to calculate y before, we need to know both the critical depth and the downstream depth. And so y2 is y after. It's after the jump is y2. So the only other thing that you have to know is the critical depth. And since this is rectangular, the critical depth is the flow per unit width squared divided by g to the 1/3 power. So solve for y before, and then once you know that, then you can find out how much the gate is opened with the given coefficient of contraction here of 60%. So it's kind of like we're starting downstream and working our way upstream to find out how much the gate can be opened. And then as a last step, we'll look at the gate equation to find out how tall is the water upstream of the gate. Like how much did it pool? All right, so starting downstream, I'm going to pause for a second and calculate the normal depth here. So we're solving for the unknown y with Manning's equation. Let's see, 10 minutes. Let's jump ahead. I'll show you the normal depth and then I'll turn you loose to work independently from that. Okay, so here's my little sketch of what's happening here. Manning's equation is what we're going to use to solve the normal depth. And so if you put in the 0.3% slope and the n value of 0.02 and the flow rate of 25 cubic meters per second, and then it's rectangular channel, so the area is 5 times the depth, and the wetted perimeter is 5 plus 2 times the depth. Okay, so just write this down. Off in the margin here, the normal depth is 1.78 meters. Okay, so normal depth is 1.78. That is y after the jump. So now that you know the normal depth is 1.78, calculate the critical depth, and then you'll be able to use the Bellinger momentum equation to find out y before the jump. Once you know y before the jump, you'll use the coefficient of contraction to calculate w, and then once you know w, then you can use the gate equation to find out what's the depth behind the gate. All right, so I'm going to stop talking and let you start calculating. When we calculated the normal depth, it was 1.78, and since the critical depth is 1.366, then that means it's subcritical flow downstream, and so it is going to go through a hydraulic jump. So using this formula, you're going to find the depth before the jump, and what you should get from that is 1.022. Let me pull it up just to show you. Okay, we previously had determined the normal depth 1.78. You can see the calculations for getting to the critical depth as our second point here. Now, the maximum amount the gate can be opened is going to be determined by the depth upstream of the gate and also the contraction that happened. So we use the jump equation to find y before, and then use y before and c sub c to find w. Okay, so if the critical depth is 1.36 and after the jump it's flowing at the normal depth, then that tells us the depth before the jump is 1.022 meters. All right, and so the coefficient of contraction is 0.6, which means that the gate must be open 1.703 meters. All right, so I think that we've addressed everything in the example in this, this first bullet point. How much can the gate open without drowning? If you open the gate 1.703 or less, then the hydraulic jump will either be right in front of the gate or pushed further away. Because, you know, if the gate was only opened 1.5 meters, then that would force the hydraulic jump even further away from the gate. And the reason why it would force it away from the gate is because there would have to be gradually varying flow until the depth upstream of the hydraulic jump matches the sequent depth to you know, the normal depth that it's looking for. Now, the second part of this example is the depth behind the gate. So we know what the gate opening height is going to be, and so we're going to be solving for y1 in the orifice equation because it's carrying 25 cubic meters per second, so Q is known, and the discharge coefficient can be calculated since we've got the coefficient of contraction. So the depth behind the gate, you can see that the coefficient of contraction and the ratio of the depths are the two components of the C sub D. And we've got the gate width and the height of the opening of the gate. So, you know, just solving for the unknown depth, which is going to be in three locations. It's here is y1, here is y1 because it's in both of those locations for the coefficient of discharge. And it's also in the orifice equation part of it. So once we use solver, then the depth should be 1.883 meters. All right, it's 1:48. I promised to let you out at least 1 minute early, and by goodness, we've done it. Let's just glance at the announcements one last time. The homework is due on Friday, then you got the final project on Monday. So if you've got questions, call me on Teams or you can send me an email. And that's it for today. Take care, everybody.